Hey geometry, what's going on? It is section 1.3. We're going to talk about polygons and other figures in the plane today. Okay, so new notes section means new learning target. Go ahead and take a second to write that down so you know what your notes are talking about today. We are going to be able to identify and measure certain elements of a polygon. Okay, and then success criteria. You'll be successful today when you can define polygons, when you can classify them as two-dimensional or closed figures. We'll talk about defining regular polygons. We won't construct them again. We don't have the tools since you guys are not in the classroom, unfortunately. And later on, we're just gonna get the basics today, and then maybe on Wednesday, we'll talk about modeling complex figures and estimating perimeters and areas, all right? So take a second, pause if you need to, we're going on. Polygon. Hopefully you have heard this word before. A polygon is a closed figure. You think of like a square or a triangle or a rectangle, all right? A closed figure formed by 3 or more line segments. All right, so again, 3 is your minimum because check it out. Here is a triangle. There's 3 line segments, 1, 2, and 3. But as soon as I take away one of those line segments, that's not a polygon, right? Again, we're looking for a closed figure. This is an open figure, not a polygon there, okay? Each segment intersects exactly 2 other segments only at their endpoints. So again, if I throw up here's a square, well, a nice looking diamond. Maybe it's not a perfect square or perfect diamond, but check it out. All of these segments here, this side, it intersects with only 2 other segments exactly at their endpoints, right there. So the non-example that I'm thinking about is, it's a closed figure, right? It's made up of 4 line segments, so it should be considered a polygon. But again, if you're looking, let's take a look at this segment right here. If I look at this segment, it intersects 3 times with other segments, right? We've got an intersection right here, we have an intersection right here, and we have an intersection right here. It can only intersect 2 segments only at their endpoints, all right? Not in the middle of the segment, only at their endpoints. So those are 2, an example and a non-example that you may want to get down in your notes. Pause if you need to, we're moving on. Okay, so non-polygon, again, that was a good example of a non-polygon. Anything that does not fit that or previous definition, basically. All right, take a second, look at these shapes. You may want to pause and make a guess of your own. Are they polygons or are they not polygons? Let's start with the first one. Check it out. It's a closed figure. Okay, we're good there. It only intersects, the segments only intersect at other segments' endpoints. So we're good there. It's made up of 4 line segments. Check it out. That guy is a polygon. So I'm going to give it a nice little check mark. Woohoo! What about B? If you look at that second one in from the left, it is a closed figure, but what the heck is going on here? Line segments are not curved last time I checked, so that's going to be a big no. All right, sorry, you're not a polygon. Too bad. Try again. Okay, C. Whoa! Again, what is going on here? I don't even know. We're missing a line segment. It intersects way more. That's just no, okay? No. Good try. D. Does it tick all of your boxes? I think it works. It's a closed figure. Nothing intersects, kind of like what we were talking about here, right? Nothing intersects other than their endpoints. I'm thinking we're good to go. Made up of 3 or more line segments. That looks like a polygon. This. Okay? It may be a polygon if you drew something like this. I think that's actually pretty good for freestyling it. That would be considered a polygon if I close that little right there. That's a polygon, but here, again, we're seeing those intersections at more places that are not the endpoints of segments. So, not a polygon on that, but I'll give that guy a check mark. That was a pretty nice star that I drew there. Pause if you need to. I would highly encourage you get some of these examples down. Maybe you make yourself a little table with polygons and non-polygons, so you know the difference. Moving on. Classifying polygons. So, I mean, we just had a whole bunch of examples, but how would we call them? Whatever they're called. All right, here's a good way to tell. When we're starting off with a simple number of sides, we can use these basic definitions and basic names that we had since kindergarten. So, triangle, 3 sides. Tri, right? You think 3. Quadrilateral, all right? 4 sides. Again, now I'm seeing this prefix of quad, all right? Quad meaning 4. Underneath quadrilateral, we will get to this. This is an entire chapter of its own. Okay, okay, here's the cool part. Triangles take up like 5 or 6 chapters in our book. Quadrilaterals are another chapter or 2 on their own. There's a whole bunch of things underneath quadrilaterals. Diamonds, rhombi, kites, squares, rectangles, any other random ones that you could make. So we're just going to call it, just in general, it's a quadrilateral. Pentagon, again, use those prefixes, not an English teacher, you know what I'm talking about. Penta, 5, hexagon, 6, all right? When you start getting into some crazy ones, like maybe you've got a closed figure on the plane and it's like 10 sides, all right? That would be like a, what is it called, decagon? Then yeah, you get a name for that. But if you had something with 36 sides, okay, so again, n is a variable, so it could be any number of sides. Let's just say 103 sides. It's just, that's too crazy to find a name for it. We're just going to call it 103 gon or a 42 gon, all right? Again, polygon, poly meaning many, so many-sided figure, you can think about it, all right? So, n-gon, if you have n sides, 103 gon, 42 gon, 51 gon, you get the idea. Fantastic. We're moving on. But I would get some of these basic ones down if you need, okay? So pause if you need to, we're moving on. All right, we've talked about naming line segments. We've talked about naming angles. Now, this is how you name polygons. You're going to list the vertices, okay? And I don't think I've said this before, but vertices are just the endpoints, right? So here's a vertice. It's where 2 segments meet, all right? Here's another vertice. It's a corner. Here's a vertice, here's a vertice. You're going to list those vertices in order, and then you can choose clockwise or counterclockwise. Again, these are just points. So when you're naming a polygon, you need to give some names, or you need to give some points to it. So I'm just going to be very basic and call this A, B, C, and D. All right? I gave my points some names, and if I want to name this quadrilateral, I want to name this rectangle. Again, we're listing all of them in order, either clockwise or counterclockwise. So pick one and stick with the directions. So A, B, C, D, that works fine. You could go the other way. What about A, D, C, B? That's totally fine. Again, I picked one and then I stuck with that direction and I kept going, all right? If I picked a different, let's pick C. So I could say C, let's go this way, that would be counterclockwise. I could say C, B, A, D. Or I could say C, D, A, B. All of these are good to go. These are all fantastic ways to name a polygon. If I said B, D, A, C. Did I pick a vertice and stick with the direction? I picked B. Did I go clockwise or counterclockwise? No, I went B, D, A, C. I did not pick a direction at all, so that is not a good way to name it. Again, you got to be careful. If you wanted to name this A, B, D, C, you can't do that. You got to stick with A and choose a direction. Stick with A and choose a direction, all right? So many times I see on homework, on tests, on anything we're talking about, a lot of people just like to get stuck in the fact that we read left to right, which is true, but again, A, B, don't go back here like a book, all right? Pick it, stick with the directions. Don't say A, B, D, C, all right? Okay, moving on. All right, and then there's this other thing called regular polygons, okay, and that's that right up here. Regular polygons are everything that you saw in like kindergarten. So look at this triangle, the classic triangle. It just looks so perfect. The square, a classic square, looks so perfect and so nice and neat. The reason why they're called regular is because all of their sides and angles are congruent, all right? So when sides are congruent, that means they have the same length. When angles are congruent, that means they have the same measure. So in my triangle here, that means that I could go through and mark all of my sides being congruent with a little slash. I could go through and mark all of my angles being congruent with a little slash like that, all right? So that would be a regular triangle. And more specifically, it's an equilateral triangle if you've heard that word before. If I want to mark this as a regular quadrilateral, go through, mark your sides being congruent. Another way that you can mark your angles congruent is like doubling up that little like circle thing. So you could either mark them with a slash, or you could mark them with two kind of circles like that. I will go back and forth between both of these ways often, so make sure you know that, all right? Again, pentagon the same side, that means, or the same deal. All of these would be the same, they would be congruent, again, with your angles. All of your angles would be congruent as well, okay? That's regular polygon. I also like to think they're just so perfect. They're the really nice ones to look at. They're not crazy looking, all right? So regular polygons, make sure you know that. Moving on. Again, example, check it out. All of my sides are marked congruent, and all of my angles are also congruent because they have the same measure, 108 degrees, 108 degrees. Regular pentagon. This over here, definitely not a regular polygon. This side and this side are really small. This side is huge. This angle and this angle is huge, but this angle is small. That's not regular. It doesn't look nice. Okay, last thing we're going to talk about is area. You know this already, all right? Area is any space occupied by a flat surface, like a polygon, like we've been talking about. And it's measured in units squared, all right? So that units may change. Maybe you're measuring it in feet squared, or you're looking at something small and you're measuring that in inches squared. Or maybe you're looking at like a map of something, okay? And you're looking at a big distance. Now we're looking at miles squared or kilometers squared, okay? Just know that those units may change, okay? All right, area. And then I'm going to throw out some formulas that you should already know that we are going to use later to help us calculate area. I just want you to get these down. For quadrilaterals, your area formula is base times height, something that you've heard probably a billion times, or height times width, okay? It's this distance times this distance. So I'm just going to call it height and base. Again, I usually go back and forth between height and base. Sometimes I'll call it length and width. It's the same thing, okay? So the area of my quadrilateral is whatever your height is times whatever your base is. Something you've heard probably a billion times before. What about for your triangles? For triangles, your area is very similar to that, but we're going to cut it in half, okay? So here is my height of my triangle, and this right here is the base. So area formula, 1/2 times base times height, okay? Again, when we're measuring height, it has to be from the very top all the way down to the very bottom. And if you could think about it, from the very top, you drop a 90-degree angle right there, okay? That is the line that you're looking for height, not one of these sides. That is not a true height, all right? That's just a side length. Looking truly from the base to the top, that would be your height. Okay, you guys are doing good. Hang in there. My last one that I have, where'd my eraser go? Last one is a trapezoid. Again, we're going to talk a lot about trapezoids later, but just to get the basics of it, what would its formula be? So take a look here. Now we have two bases. We have a base on the top and we have a base on the bottom, and we are also given a height. Notice how the height again drops from the bases here, okay? We're not measuring this length, we're not measuring this length, we're measuring this true distance between the top and the bottom, okay? And again, you see that 90-degree angle. So for a trapezoid, did I spell that right? Okay, doesn't matter. You know what I'm talking about. For the trapezoid, your area formula is going to be, oh my gosh, happy Monday. I'm doing this on a Monday. You're going to take the height and you're going to multiply it by the bases added together divided by 2. All right, so B1, which we could just say is the top base, plus B2, which is the bottom base, divided by 2, okay? Again, when you're kind of looking at that, looks kind of similar to, like, you can think about it, the midpoint formula. Remember in the midpoint formula, we took those bases, or excuse me, we took those coordinates and we averaged them out. Kind of the same thing we're doing here. We're averaging out the bases on my trapezoid, all right? So that's why I add them together, divide by 2, and then multiply by the height. Trapezoid. Fantastic. All right, that was all I have for you today. So please go join my Google Meets at Blackman 107, and we'll go over some review questions, and it will be awesome. Fun times to be had for all. Have a great day, everybody. Bye.